Right, going to run through the first part of the gravitational fields topic. It's fairly straightforward, but really, really important. It's the mainstay of this whole topic. So, just going to pick up on a few things. It's all about knowing this idea of fields that we're going to use, and most of this is in the PowerPoint. I'm going to quickly go through the ideas of gravity and, more importantly, Newton's gravitational law, so sometimes called his fourth law of motion, but it's just to do with gravity. Okay, we've already done some last year. We've already dropped stuff, obviously, to find acceleration due to gravity. We've also looked at parabolas. However, we're going to use the ideas that we've done from last year, GPE and all of that, to actually then start linking things together. Put the bottom one in brackets because you should have done it sometimes in Key Stage 3, so it depends, but I'm not going to assume much. So, first bit. We know roughly what gravity is, but this idea of a field. So these are forces produced without things touching. So a field is an area around, in this case, a mass. Okay, so any mass that you've got, it produces something that we call a field, where any other mass, okay, has to be the same kind of property, any other mass will experience an attractive force. Okay, so fields are where things attract. Some fields also repel. For mass, it's mainly attract, the vast majority of the time. So, yeah, gravitational field is where masses attract each other. Now, what we can do, and this is where the phrase started coming in, where we introduced it last year, we can talk about the centre of the mass. Things act as though all the mass is there, and so this field acts around that point. Now, in reality, it's slightly distorted depending on the shape, but when you get further away from the object, then the field lines that represent this gravitational field will always head towards that centre. So, for example, planet here, they're all heading towards the centre of the Earth. So that's where the centre of all the mass of the Earth is. So, we're going to use this idea. We're going to use the idea of having a test mass that will see if there is a force. If we can feel the force of it, then there must be something acting on it, which will be the field. And we can represent that by thinking about the density of the lines. So the field is more intense here than it is further away because the field lines are much closer. So that's the idea. So, two main types of field we've got here, radial and uniform. In reality, nothing's quite uniform. Things will attract around and things don't fall completely vertically, even if there is no air. And the reason is everything that has mass will distort the field. So any sort of mass or higher density of mass will cause a distortion in a field. So near the surface, okay, if we've got hills, okay, or dales, I'm going to put dips, as not everyone knows what a dale is away from this area. If you've got that in your surface, mountains, canyons, whatever it may be, you're going to get distortion near those. Okay, things will fall towards a cliff. The other thing is that not all rocks are the same, so rocks of different density, they will also cause, I should say in the surface or near the surface, they will cause distortion as well, and that's used by geologists to actually work out what rocks could be hidden underneath. So, in this idea here, what the effect of it is, the effect of a planet's gravitational field on a smaller mass is that object accelerates. And we're going to pick up on that in a bit. Accelerates due to its force due to the gravitational field. In other words, weight. Okay, so we have that phrase, but we're talking about the mass within the gravitational field. Little mass dropping multiplied by the gravitational field strength. Okay. In reality, then we've actually can't avoid the other laws. So Newton's third law means that the main object, the planet, also accelerates. And what it does is it heads off in the opposite direction, to the smaller, I'll try that again, smaller mass. So is an object falling towards the Earth, or is the Earth falling towards the object? Equally both. It's just the more massive the object, the slower it's moving, the less likely you are to notice it. So, yeah, we have Newton's third law. Masses attract to each other. However, for most of us, we have this idea that things will drop towards planets. So what we're going to do is we're going to use that as the basis of our idea that we stick with. And so we're going to consider one huge immovable object, okay, in this case a planet, and then we're going to say things will attract towards that rather than doing the other thing. So in the PowerPoint, I've told you about Schahalian, so here's an idea of it, and it's just working out the fact that we have attraction to the Earth, but again, if you've got some dimple in the surface, fairly big dimple, 1,000 meters or so, you've got that mountain of the attraction due to that mountain. So if we put those together, we can work out the resultant effect on it. So if we put those together, then we end up with a nice, carefully drawn, in your notes hopefully, parallelogram. So that's going to be the force that is the resultant. That's where our pendulum is going to hang. And if we have something large enough here with enough force of attraction, then we can actually start measuring decent angles. And so we know from testing this with masses like this, and we still do it to find density of different rocks within the surface, we can actually work out the density due to the mass of all these separate bits. So if we have a volume and we know the density of the rock, then we can work out its mass, or vice versa. Now, this is the really important bit. This, Newton's fourth law, unofficially, this is vital to the whole topic. Okay, we have two masses, they're both attracting with the same force. What Newton realised was not just apples fall towards the Earth, but so does everything else. And he realised that he could do some patterning by looking at the work of previous people where two masses will attract and the force is proportional to the size of the two masses, the product of the masses, okay, and inversely proportional to their separation. Now, this was actually first highlighted by Robert Hooke using Galileo's work. So this isn't Newton's work, and Newton did his best when he came in charge of the Royal Institute to actually spoil the reputation of Robert Hooke, but it's known as Newton's laws. Hooke was a very big genius, it's just he's often overlooked, so let's keep that in your mind. He didn't just do springs. So our force of attraction, this is Newton's law. It's not an equation, it's a relationship. Okay, two masses attracting, the product of the masses gives us the force, and inverse of the separation gives us the force. Now this, okay, I'm going to change to r squared. And the reason I'm doing that is, although it should be the separation between the centres of mass, okay, or centre of gravity, gravitational field, we tend to think of it as one going around the other, so we'll use the r for radius. Now, what 100 years later happened was a guy called Cavendish came along, and he turned it into an equation because he realised that he could work out the constant that related them together. So notice we're now becoming a bit more sneaky, and this is really important. We have a multiplying factor. We know that they are attractive, so to fit with everything that means it's negative. And when we get to electric fields, you'll see why, because it fits with everything coming together nicely. And the other thing is, we have a main mass, and then we have one being attracted towards it. So we've got the big planet, and this is the thing on the planet idea. Okay, so he did that incredibly delicate experiment because he realised and found the value for G, and G is tiny. 6.67 times 10 to the minus 11 Newton meter squared per kilogram. Rearrange that and you can get those. So newtons meter squared per kilogram. I should say squared. Spotted and mistake in my notes. So tiny, tiny, tiny. The effect of gravity is absolutely ridiculous compared to the size of forces that hold you together, electrostatic forces. It's lucky because otherwise the gravity would rip you apart. Okay, so you are held together by your electrostatic charge. Gravity, luckily, is much, much weaker. However, even better is if we can ignore the second mass. We would just want to know about the gravitational field around an object. So to do that, we've come up with a definition called gravitational field strength. Okay, that density of lines idea. The definition for it is force per unit mass acting on a small test mass, often placed at that point in the field. So basically, G equals F over little m. Okay, that equation is crucial. That's a really powerful idea, and we'll keep going back to that when we do the other fields. We want to know about the field rather than the force. We use, in this case, the mass to find the force to tell us about the field. So this is the thing that we're actually after. So not always convenient in terms of mass, but that's the big idea from this topic. Now, to round that off, of course, if we have the force there, we can simplify that. So it will give us the equation inside. So if we say that G is F over M, that equals big G minus big G, big M, little m, over R squared, and over M. So those are going to cancel. So G equals minus big G M over R squared. And that is a really useful equation. Now I should make clear that is for a radius. So this is only working for radial field. If you are near the surface of the Earth, then it is just simpler than that. You need to keep it much more simpler. Okay, so just to bring this idea, M, shall we say, creates the field. And what we do is then, and we test it with little m. Okay. Now we can go into more detail, but I'm just going to round off with that key point that actually came from Galileo again, in that the reason, again without air resistance, so in a pure example, the reason things accelerate is because the gravitational field strength acts on M to make that go downwards. So the force makes that mass accelerate, Newton's second law, simple version, and that is caused by gravitational field strength acting on M. So we have an idea of equivalence where A is equivalent to G. Things will accelerate due to G at the same rate that G has the value of. So 9.81 newtons per kilogram, that is meters per second squared. They're equivalent They're not the same thing, but it does form the basis of Einstein's work. Okay, it's known as equivalence principle. Okay, and we will leave it there because that's good a place as any. Loads of questions are based around that equation and the previous one, so know your way around these. This is where we're going to use it quite a lot, but those are really important. So have a go at plenty of the questions that are in the back for section 1 of the topic.